Next up we have electronegativity, dipole moment, and then percent ionic character, which we're going to kind of gloss over some of those a little bit. But electronegativity we've already hit. I've already talked to you about electronegativity. We talked about electronegativity as it relates to electron affinity. So let's just kind of talk about electronegativity. Again, electronegativity refers to how tightly those electrons are held to itself when in a bond. Okay. Bonds can either be polar, like magnetic poles, North Pole, South Pole, or they can be nonpolar, where the charges are all distributed pretty evenly. Okay, those are called nonpolar. In ionic compounds, they're going to be quite polar. But covalent compounds can be either polar or nonpolar. So let's visit those for just a minute. Here we have some non-polar and some polar compounds. And again, the one on the far right, sodium fluoride, is very, very polar. And I don't see too much of a need in us discussing those very much, because ionic compounds, that ionic bond is going to be of a very, very positive end. That's the cation end. And it's going to have a very, very negative end. That's the anion end. So it's always going to be very polar. Positive, cation, negative, anion. Very polar. And so it's going to always be held together by those opposite attractions to each other. Okay, so let's focus on the left side in the middle. That's, to me, more important. So let's talk about electronegativity and how that relates. Electronegativity, again, I explained it kind of this way with my sister. My sister and I were close in age, so we always ended up having to share a house because there were 4 kids in our family. And so, you know, you can hardly ever find a 5-bedroom house. You can find a 4-bedroom house, though. So my sister and I, because we were the youngest, we always had to share. And so we always, whenever we bought stuff, we always had to share in our bedroom. And my sister would always say, you know, well, let's put it on my side of the bedroom. Let's put it on my side of the room. And she was the youngest, and so my parents would always say, you know, let her have it. She's the youngest. And it would always, you know, it caused some true sibling angst there for a long, long time. So that is electronegativity. You know, who's going to get it on our side? If we're going to share these electrons, who's going to get to keep them closer? So in this case, hydrogen. Let's draw the electron dot structures for both of these 2 hydrogens. Here's this one's hydrogen, and this one's electrons. Now, if both of these are pulling on those electrons just as hard, and they are because they are identical, then who's going to win this battle? Nobody. So since nobody's going to win this battle of the electrons, these are truly going to be shared evenly. And if these electrons are going to be shared evenly, then this is going to be non-polar. Nobody's going to win. That charge is going to be distributed evenly throughout this. And you can see that by the even egg shape here. Okay? If you have a polar compound, as you have in this case, here we agree that these 2, hydrogen and fluorine, are saying, hey, we're going to share these 2 electrons. Hydrogen and fluorine agree that they're going to share. Fluorine needs to gain 1, and hydrogen needs to gain 1 so that it can be like helium. Fluorine wants to be like neon. So here's hydrogen's 1, and here's fluorine's 1 that it's going to share, and there's its other 7. The difference is, remember, Fluorine is the most electronegative on the whole chart. So who's going to win this war? Who's going to say, I'm keeping them in my room. I'm going to keep these electrons closer to me. It's going to be fluorine, I guarantee it. So fluorine's going to say, yeah, I'll share with you, but we're keeping them closer to me. So even though hydrogen's right here, here's hydrogen's electron that it's willing to share, and there's fluorine's electron. And you see the kind of gap that I've put between these two. So even though they're sharing these electrons between them and there's a bond there, fluorine's keeping them close to itself. This is what electronegativity is. The tendency of an atom to pull those electrons to itself during bonding. This makes the atom feel like it's got charged ends, even though it doesn't, because these electrons are being shared between the two. It makes it feel like it has a positive end. So here's the hydrogen over here. Where's its electrons? It's in there being shared, but where are they being shared? Way over here close to the fluorine. So this, I'm not very good at drawing these. This is called a sigma. This feels like it's got a positive end, and this end feels like it's a negative end. That's what it's called. Partial. It feels like a positive end. It feels like it's got a negative end because of this unequal sharing of these electrons, because fluorine's being, bullyish and saying they're staying over closer to my house, to my side of the room. Okay, notice here's the textbook definition of electronegativity: the ability of an atom to draw the electrons to itself. That's what I was trying to kind of explain, that they're going to stay on my side of the room. And how do you know which one's going to win? The ones that have the higher electronegativity. Which ones are those? Think about those. Think about that for a minute. We talked about that in Chapter 7. The ones closer to the right on the periodic table and farther up in a family. So the ones farther to the right and higher up in a family. So the highest electronegativities are ones like fluorine, oxygen, chlorine. Those guys right there have the highest electronegativity. Okay, so if those guys are involved in a bond and they're sharing with somebody else, that's going to probably be a polar. And what does that have to do with anything? Everything. Because we use things like that. Your clothes soap uses properties of polarity, because water is very, very polar. Very polar. And the fact that water, because think of what it has little puny hydrogen and very electronegative oxygen. And so it has a very positive feeling end and a very negative feeling end. So it's very polar. And that gives water extremely unique properties. Very high boiling point. And so when you put clothes soap in your water, like dissolves like, so you need to put some clothes soap in there that's also polar. But what are most stains made out of? Oils, like our oily skin, and oil is non-polar. So you need your clothes soap to be polar so it will dissolve in the water, but also non-polar so that it will stick to the oils and grease that most stains are made out of. So clothes soap is made out of things that are partially polar end and partially non-polar end. So, it's in everything. It's quite impressive. So here's a periodic table that shows you where increasing electronegativity up a family and over. And notice here, this is what I was telling you. Fluorine, oxygen, these are the guys that have chlorine. These are the ones that have the highest electronegativities on the entire chart. So they are going to be the ones that are going, if they're involved in the bond, they're going to have highest electronegativities. All right? And so this here again is her numbers. She really likes these numbers. So if you have these electronegativities, if you have two atoms and you're looking at these charts right here, and you have a bond, let's say, between nitrogen and oxygen, let's say, she is saying that that's probably going to be nonpolar. But if you have a bond between hydrogen and oxygen, that's going to be polar, because the bond, here's what she's saying right here, that if the bond electronegativities differ by less than a half, then it's nonpolar, okay? But if they're polar covalent, if it's between a half and 2, and then if it's more than 2, it's ionic. But if you got a metal and a non-metal, or a polyatomic ion in there, it is ionic, and it's going to be for sure ionic. But you need to worry about, is fluorine involved, or do you if you have 2 fluorines, 2 identicals, well, it's going to be nonpolar. You got to worry about, is that charge spread out evenly? Okay, so in this case, you should be able to figure this one out. If you have chlorine and fluorine, and it gives you the electronegativities, just so that you can help. But see, fluorine is a big bully here, so I hope that you could be able to see that that's probably going to be polar towards fluorine. And then cesium and bromine. Cesium is number 55. It's a metal. So if I have a metal involved, well, that's a cation. It needs to lose, so that's going to be ionic. And then you have a carbon-carbon, and it's only asking about between the 2 carbons. So if I've got carbon and carbon, then those 2 are identical to each other. So that's going to be, since they're identical, both of them are both carbon, that's going to be nonpolar. Okay? All right. I hope that you're getting that. Okay? And then this is talking about dipole moments. And this is just talking about which side is going to be my more positive end, and which side is going to be my more negative end, and that's called your dipole moment. Okay, and it's showing you using this cross-looking thing, and it's showing you your dipole arrow is pointing to which end is going to be more electronegative. You see that symbol right there? That's what you're going to show is going to be it's going to be more polar towards your more electronegative. So the arrow is going to point towards your more electronegative. And obviously, if it's more electronegative, it's going to be the more negative end. Okay? I'm not going to worry about, we're not going to talk about the actual value of your dipole moment. We're not going to concern ourselves with that in this chapter. Okay? But you can talk about bond length there. Please keep in mind that bond length is going to be shorter in double and triple bonds, longer in single bonds. All right. There's a table for them, by the way, in the back of your text. And then this is talking about how ionic and what percent is the ionic character going to be. And obviously your ionic bonds are going to have the most ionic character and the more electronegative, like, for example, in this case, you have lithium with fluorine. Well, fluorine's very, very, very electronegative. So if you have a metal with fluorine, it's going to be extremely ionic, and so on. Okay? And then we're going to work on drawing Lewis structures. And this is a big one right here. This is probably the meat and the heart of this particular chapter. So drawing Lewis structures. Please know that this is exactly what you're going to do. The first thing you're going to do is you're going to write your molecular formula, and then you're going to draw what's called a skeleton structure. We're going to use those the symbols, and you're going to draw lines to represent the bonds. Please remember that you're always going to put whichever is the least electronegative as your central angle. Now again, so many of you have already done your molecular geometry lab, and if you've done that, then you already know almost all of this. Remember, hydrogen always has to be on the end. It can never be in the center, because hydrogen only has 1 electron, so it cannot form anything but 1 bond. So it can never be in the center. And then remember, you're going to count the total number of electrons. And remember, you're going to worry about your polyatomics as well. And if you have polyatomics, you have to include their charge with the total electrons. Like for sulfate, for example, sulfate has a -2 charge. That means it has 2 extra electrons. You have to add those in to your total electron count. You have to do so. For ammonium, it has a +1 charge. You have to remember that. You have to remember to subtract 1 electron from the total number. Okay? And then for every time you draw a dash, you're going to take away 2 electrons because a dash represents 2 electrons. So if I'm writing we're going to do an example here in just a minute, but then how many electrons do we have left over? Okay? And then you're going to use those electrons to make your octets, your 8, around your central atom first, and then around your terminal atoms, and the terminal atoms are those at the end. Okay? And notice what it says down here on the bottom of number 4. This is an important tip. Okay? If you have more than one type of terminal atom, remember what a terminal atom is. It's an atom that's bonded to your central atom. Okay? You do those first. Do the one that's the most electronegative first. Alright. Okay. And then if you have your central atom still has less than 8 electrons attached to it, you got to go and find 2 more to put on it so that you can complete its octet. Okay? Alright, so here's an example. It asks you to draw the Lewis structure for carbon disulfide. So here is the structural formula. The structural formula for carbon disulfide is, the molecular formula is CS2, and the structural formula is SCS. Why? Because carbon is less electronegative than sulfur. How do I know that? Because carbon is further left, sulfur is further right. So the more electronegative is further right. So carbon is almost always going to be your central angle every time. So I'm going to put carbon is my central angle, so sulfur is my terminal. So to do this myself, I would have to draw my electron dot diagrams. So here's my Lewis structure for carbon, and then sulfur, each of them have 6 valence electrons. So I have 2 of them. There's sulfur 6, and here's this sulfur 6. And notice that my 2 sulfurs on the ends, they're already happy because each of them is feeling its octet. Each of them is feeling 8, but my carbon in the center is not. But notice what step 2 is right here. My total number of valence electrons. This 2 right here means my 2 sulfurs. Each one of them has how many valence electrons? 2, 4, 6. You know that because it's in group 6A. And then this 4 right here is from my carbon, my central angle. So I have a total number of 16. Okay? Now, in my skeletal structure, I put a line there that represents 2 electrons, and this one represents 2 electrons. So that represents 4 electrons right there. So that's what it's talking about right here. Subtract 4 from that 16. That leaves us 12. Because each line right here means 4. Okay? Alright, so now I'm going to take those 12 left over and I'm going to distribute them, which is exactly what I did. I distributed them, I drew them so that I have 6 around each carbon. I had drawn them on the other page. There's my carbon, and there was that line and that line, and there was that sulfur and that sulfur, and I had 6 around each of these sulfurs, if you'll remember. That's what I had. But there's no leftover electrons, so that should be good, except that my carbon, my central atom, does not have 8. Okay? So that is not okay. I've got to figure out a way to make my carbon have its octet. So I've got to complete my carbon's octet. So I've got to take 2 from around each side, which means I must remove 2 from here, and I must remove 2 from this one as well. And when you do so, keep in mind that those remaining want to stay as far from each other as possible, which is why they put these electrons on the sides the way they did. Now, please keep this in mind. I noticed that several of you said that because this had 3 on your models that you did, your model lab that you did, you said that this, oh please, I'm sorry, that this had would be bent, but because of this double bond right here, because this has 2 double bonds in it, it cannot be bent. It must be linear. Those double bonds are very strong, and they won't allow this particular molecule to bend. So that has to be linear. I don't know why that this page turned. I don't want it to turn. Now, you saw that the next page talked about formal charge, and formal charge is helpful, but I think you need a little bit more practice myself. This is what I was talking to you about right here. These moving to the side, instead of where I had them at first, I had them here. They started off being here at top and bottom. The fact that these bonds are here, these electrons here, these unshared electrons, or lone pairs of electrons, are going to move far away from each other. And those paired up electrons literally push or repel, so that these unbonded electrons, their lone pairs, want as much space, and so they get pushed. And these 2 double bonds right here force, there's a very strong and very short, they force this to be a linear shape. And we'll get to that more in chapter 9, but this is a linear molecule. All right? Now, formal charge is something that she talks about, and I will go into it somewhat, but you need practice with these. It takes some time. So, formal charge can help you when you're learning how to do electron dot structures. But it helps you because it is just, if you take the number of valence electrons, the total number of valence electrons, and then you talk about those electrons that are associated with your central atom, then that's called your formal charge. And this is kind of your of a way that you can find your formal charge. Now, formal charge is not completely necessary, but it is helpful if there's more than one way those electrons can be distributed to find the best solution for it. And so here's what I'm talking about. Here is a resonance structure for ozone. This is ozone, and you can see right here. Here's ozone. Notice we have 3 oxygens. Each of them has 6 electrons valence. So that's a total of 18. Okay? When we put these around our central angle, whichever one it is, and we, so if we have this oxygen, this oxygen, this oxygen, and we go ahead and we make them, then what we have here is we have our unshared, and then we talk about how many are shared. We have 2, 4, 6, these 2, 4, 6 that are shared, and divide it by 2. And then how many are left over are only around our central, only around the central atom. This oxygen right here is the central. 2 unshared. Okay? 2 unshared. That's what's going to give you, and then you're going to subtract that. So you have 2 unshared. 6 divided by 2 is 3. So 2 plus 3 is 5. 5 electrons. Okay? 5 electrons. All right, then let's talk about, that's your central angle. That's your central atom. Now let's talk about the associated atoms. Okay? You have 4 that are unshared on the left one, on the left oxygen. And then you have 4 that are shared with that middle one. Okay? If you see what I'm saying, I'm going to change pen color so that I hope that maybe it will become a little bit more clear to you. You have these 4 that are being shared, and these 4 that are unshared. So that's 4 plus 4 divided by 2 is 2. So you have 4 plus 2 equals 6. And you have, on this one over here, you have 6 that are not shared, and only 2 that are shared. So 6 plus 2 divided by 2 is 1. So this is 7. Okay? So let's talk about the total numbers here. How many valence electrons does each one have? Each one of these oxygens has 6. Okay? Let's talk about the number associated with each one. Okay. In this case, on the one on the far left, so this one right here is the left oxygen. 6 minus 6 is 0. So this formal charge on this left oxygen is 0. Our central atom, 6 minus 5, is 1. So this formal charge is 1. And then 6 minus 7 is negative 1. So the charge on this right hand oxygen, the one on the right, this one right here, is negative 1. So the goal is that you want your formal charge on the overall molecule to be 0 or as close to 0 as you can get it. And notice that 0 and a positive 1 and a negative 1, if you add all those together, your overall charge, formal charge, is 0 for this particular one. So the closer that you can get it, the formal charges got to add to be 0, and for ions, it's got to add to be the charge on the ion, but look what she's saying right here. When there's more than one possible skeletal arrangement, the best skeletal arrangement, a Lewis structure in which all the charges is preferred. So if you can get all your charges to be 0, it's going to be better. So small formal charges are going to be better to larger ones. And she gives you an example right here. Notice this one. So this has a 0, a negative 1, a positive 1, and a 0. And this one, all the formal charges on this one, when you found all of those, they were all 0. So this bottom one, these are both the exact same element, the exact same compound. Which one would be right? The bottom one, because all the formal charges are 0. So when there's more than one way that you could do your Lewis dot structures, choose the one that's going to give formal charges that are smaller or 0. That's what it's saying. All right, I really went long on that, and I'm going to quit for now.